Shall we? Good afternoon. The last time we talked about chemical bonding, and we have done this for quite a while, we talked about Lewis structures, and you have found out, I knew that already, you have found out that there are more than one valid Lewis structure for certain compounds, for certain molecules. We have had ozone, for example. Ozone has 3 oxygens, and you see there's a double bond here and a single bond here. That means there are 4 electrons here and 2 here, and this is a valid structure. 2, 4, 6, 8 octal rule fulfilled here, 2, 4, 6, 8 octal rule fulfilled here, 2, 4, 6, 8, there's 7 only here. No, 2, 4, 6, 8 octal rule fulfilled. Counting. It's Friday, isn't it? Yeah. And there is a big holiday coming up on Monday. Don't use the Bay Bridge actually, because it will be closed in one direction. Okay, so coming back to your attention. So you see there's a double bond and there's a single bond. You could have also, this is a valid structure, and this is a valid structure because you put the double bond over there. So these are resonance structures. So the truth is somewhere in between, and that means it's not a double bond, it's not a single bond. A double bond has bond order 1. We define, I think, a double bond has bond order 2, a single bond has bond order 1. Okay? So this must be somewhere in between because we have one single bond for each of them and one double bond to share between where the 2 bonds go. So this, we split this in half, so then the bond order is 1.5. So it's not a double bond, it's not a single bond order is 1.5. All right? So with this we have seen then, there are several ways to do this, bond order 1/3, 1.5 again, and we talked then about formal charge. So when you have a structure, a Lewis dot structure of a molecule, in order to formal charge, to define the formal charge, is the number of valence electrons in the free atom minus the number of valence electrons in the molecule of the atom, okay? So the free atom we know, and in the molecule we have to determine what that is. And with this we get the formal charge, and this formal charge will help us to decide which one is the more likely structure, or the more correct structure when you have several structures. And I will give you an example about this. So you assign the lone pair entirely to the atom when you do this formal charge determination, and so far we know only nitrogen has a lone pair, and nitrogen always has a lone pair, so you assign this to the atom. Shared electrons are divided equally between the sharing atoms, so you split them in the middle. And atoms with molecules try to have formal charge. Now, okay, we talk about this later. All right, so let's do something about this here. So we have the Lewis dot structure, and you know this is NO2 minus, and we have done this quite a bit. This has, of course, a resonance structure, because you see this is a double bond and this is a single bond, all right? But in this case, both of them are valid, so I want to determine what is the formal charge. The formal charge on this one here would be, so we say we share the electrons equal to 2, 4, 6, 8. This would be 8. And how many you have in the atom by itself? How many electrons you have in the atom? 6, okay? So they have 2 more, that would be minus 2, is that right? Okay. Now let's look at that nitrogen. They share equally. So this one gets 2, the nitrogen gets 2, the oxygen has 2. So actually this was wrong what I just told you, okay? I didn't share equally. So if I share equally, would be the oxygen. Let's rewind this, not my date, okay? When the oxygen here, we share this equally, so we take 2 to the oxygen, so we have 2, 4, 6, and we compare it to the free atom, it's also 6. So the formal charge would be 0 for that, okay? You got it? You're with me? Because I wasn't with me, all right? So, all right, so the formal charge is 0. Now let's look at that oxygen. We split that equally, so that gets 1 to the nitrogen. So this oxygen has 1, 2, 3, 4, 5, 6, 7. 7. So what is the charge in the free atom? 6. So this has 1 more, the formal charge would be minus 1. Is that okay? And let's look at that nitrogen now. So this one, there's only 1 here and 1 here, because this went to this oxygen, this went to that. So this is 4 for the nitrogen. What's the number of electrons in the free atom? 5. So what is the formal charge with this? Plus 1. Okay, good. Now let's do that. N is the electrons are equally shared here, is 5. And here it's 7. 7, we established this. That's 5 in the atom, in the unbound atom, and in the unbound atom here is 6. So this gives us then the formal charge. Here we said it's 0, and here we said it's plus 1, minus 1. Okay, minus 1. Let's see if this is true. Sure enough. Okay, all right. So you know now about formal charge, and I give you here your roadmap. And why don't you answer that question? So we have NO2 and NO3. We did this the last time. The nitrite and the nitrate, nitrate and the nitrite is nitrite and this nitrate ion. So it's an oxidation of NO2 minus to NO3 minus. And I'm asking you, how does the formal charge of the nitrogen? I want to know the formal charge of the nitrogen. How does this change when you go from here to here? Does it increase, stay the same, or decreases? So why don't you draw the structure, and then you go with these rules and find out what the formal charge is on the nitrogen. Looks like I need coffee. So nitrogen has 5, oxygen has 6. You have 1 extra one, so that's 2 times 6, and 5 is 17. It's an 18 electron, and this other one is a 24 electron system. Okay, let's have a look at this. I can't say it any more clearly than I did. So if you have a plus 1 compared to a 0, would it be an increase or a decrease? Increase. And if you have a minus 1 compared to a 0, would it be a decrease or an increase? If you're 0 to minus 1, would be a decrease, okay? Now you're completely confused, and now you need to discuss this with each other. You really need to get this right. So the NO2 we just did, didn't we? NO2. Why don't I give this back to you, okay? All right, no NO2. Yeah, there's the NO2 right there, okay? So then put the NO3 in there. Yes, we discussed it now, but I need to start it. Whoa, I need that vacation. Thank you for telling me. He was very kind. He said, are we discussing this now? He said, hey, you forgot to start it. Can you hear me in the back there? Sir in the blue shirt, you can hear me? You can hear me? Good. What's your name? Anyhow, nice to meet you. Does it increase or decrease or stays the same? What does it do?
No.
If you go from this to this, does it increase, stay the same, or decrease? The formal charge on the nitrogen. What is it? Huh? No. You guys are already on vacation, huh? Can't blame you. But I explain it to you, and then you say, why couldn't I get that? Yeah, we're getting better. That's wonderful. No, actually, we're not getting better. We're getting worse. So that's the answer here. A, okay? All right, so let me explain it to you. Let's do this very slowly. I want everyone to understand that. Everyone, okay? So we have here, oh, there it is. Let's do the formal charge of the nitrogen for this one, okay? So we split it evenly, so there's 1 here and 2 here. You're with me? And we have 2, so there's 4, 5, okay? 5, and we compare it now to the free atom. How many valence electrons do you have in the free atom? 5. The difference is 0. That's the formal charge, okay? Now let's do this one here. This has 2, then this one has 1, so this is 3, and this one has 1, this is 4. Is that right? You see that? There must be a double bond. Remember NO3, we did that. That's a valence structure. That's a double bond and 2 single bonds. And so this is 2, 3, 4 on the nitrogen. You already said it. How much is the nitrogen? How many valence electrons you have in the free atom? 5. So what's the difference? Plus or minus 1? Plus 1, okay. So, we did that right. So, so this plus 1. So if you go from 0 to plus 1, is it an increase or a decrease? It's an increase. Okay, good. Did you get that? No? So what shall I do? What can I do? Now you make me feel bad, okay? So you come to my office hours, you will go to the GSIs, you come to open office hours, you go to the review on Thursday evening. Excellent, who was there last time has a big benefit last Thursday, because there will be a question in the midterm, which was very well discussed there. Okay, now you gotta ask, what did they discuss? Now, maybe you understand it now. We have, everybody is with me, okay? We have cyanate, that's the cyanate ion, OCN minus, okay? So we have structures that how many electrons does this have? 6 for the oxygen, 4 for the carbon is 10, 5 for the nitrogen is 15, 1 minus is 16. Are you with me? Yeah? 16, everybody is with me? Good, we have it 16. So this is a way to do that. 16 electrons. Let's see if we did it right. 2, 4, 6, 8, 10, 12, 14, 16. Good, all right? Let's look at the formal charge of the nitrogen. This is 2, 4, 6, 7. 7 electrons compared to the free atom. What's the formal charge? What's the formal charge? Minus 2, because you have extra electrons. That's minus 2. What's the formal charge on the carbon? 0, okay? And the formal charge, this is 1, 2, 3, 4, 5. The formal charge on the oxygen? Plus or minus 1? Plus 1, excellent. There it is, minus 2, 0, 1. So we need to minimize the formal charge on the individual atoms, and the negative charge must be on the most electronegative atom. Okay, so that minus 2 is on the nitrogen. But what is more electronegative? The oxygen, okay? So this is not very good, right? Let's do the next one here. What's the formal charge on the nitrogen here? 2, 4, 6 compared to the free one? What is it? Plus 1. No, minus 1. Good, you got it, minus 1. On the carbon? And on the oxygen? 0. Okay, let's see. Minus 1, 0, 0. We're doing okay. You're learning formal charges. Now, would that be okay? The most negative, the negative charge must be on the negative atom. Electronegative atom. Is this a good structure? No. But you want to have a small formal charges on individual atoms are better than large ones. So there's no more 2 here. That's already a little bit better. But we minimize also the formal charges on the individual atoms. So that would be minus 1. We have minimized it compared to here. But it's not good. So let's look at this one here. We have 2, 3, 4, 5. Nitrogen, what's the formal charge? 0. Carbon, what's the formal charge? And what's the formal charge on the oxygen? Negative 1. Would that be a good structure? Yes, that follows all the rules. Good. Now you're getting formal charges, aren't you? Okay, excellent. All right, and you see that if you add this up, this is minus 1, this is exactly minus 1 here. All right, this has to be, of course, minus 1. All right, so what's going on here? Yeah, just for completeness, I want to talk about this. We're not going to discuss this in detail, but some of you heard of oxidation states. Who heard of oxidation states? Excellent. And probably in the book, I haven't looked at it, and there's probably some explanation at the same time when they explain formal charges about oxidation states. And we will use this when we talk about redox reactions. We're not going to use this in the next midterm, okay? I just want to briefly touch on it, and I will bring it back when we do redox reactions. But there's another way to get an oxidation number, and this gives you distribute the electrons by electronegativity. So the more electronegative gets all the bonding electrons, okay? And with this here, you would have the oxygen would have 2, 4, 6, 8. Okay, this will compare to the free atom. What would be the oxidation number? Minus 2, okay? And the nitrogen, okay, that has been taken here. The nitrogen has been taken. This takes this here. And this would be the nitrogen. What would be this here? There's only 2 left of the nitrogen because this is more electronegative, takes all this one. This is more electronegative, takes this one. So how many would you have on the nitrogen? 2 plus 2 compared to 5. So what's the oxidation number? Plus 3, exactly. There we go. That says, okay. All right. Did we say plus 3? How can we say plus 3 if you have 8 and compare the oxygen as 6? For the nitrogen plus 3. Okay, yeah, that's correct. But that's okay. For the nitrogen plus 3. I need a break. Okay, plus 3. All right. But it's going to get better, you know. And this is minus 2. Are you with me? Okay, oxidation number is not the same as formal charge. Take it out of your head. All right? We take it when we talk about redox reactions. Formal charge, keep it in your head. All right. So today, we're going to talk about how the molecules, so far we have flat molecules. They're in 2-dimensional in paper. They have these structures, these dot structures, but we have negative charges. These electrons have negative charges. So if this would be carbon here, if you could get a full shot of me, please. If this would be carbon here, okay, and this would be an electron pair, and this would be an electron pair. So I stand like this, okay? So here and here would be whatever would be the partners there. And in this case, it would be maybe carbon and 3 hydrogens and 1 other carbon, all right? So, but this is negative, and this is negative. So is this the best separation of the negative charges? Is that the best separation? What should I have to do? This would be the best separation, okay? And this is how sterically it's done, because now the repulsing charges, the negative charges, are as far as possible away from each other. But this would be also okay, just that I don't go limp here. All right? And so you see, it's a steric configuration. They are not flat. And if you look at this here, for example, so we can go back to the screen. If you look at this here, so that carbon has 1, 2, 3, 4 bond partners. Okay? That carbon has 1, 2, 3, 4 bond partners. 2 hydrogens, 1 carbon, 1 oxygen. This oxygen has 2 bond partners and 2 free electron pairs. All right? But hydrogen has only 1 bond partner. So I want to determine a steric number. And you will get the hang of this once we are done today. Steric number is the number of lone pairs plus the number of bonded atoms. So what would be the steric number for carbon here in this compound? 1, 2, 3, 4. You have 4 bonded atoms, no lone pair. Steric number would be 4. You agree with that? Okay. What would be the steric number for that? 4. And the steric number for that? That's very good, because you have 2 lone pairs. Each lone pair counts for 1. It's the number of lone pairs, but the number of bonded atoms. Okay, and the hydrogen, of course, would be only 1. So now let's do something here, and let me get this to you here. And I'm going to switch that off here. So we have here balloons. And I'm going to explain to you now how you can bind things together. You have here, Cal Collins, go Bears. Go Bears, okay? All right, so we have here, where my hand is in the middle here where my hand is, there's the central atom, yeah? And this we see is the bonds here. That's the bond. So there's 4 in this plane, this is we call the equatorial plane, and 2 of them on the axial plane, okay? And so there can be 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. What's the steric number? 6. Actually, you just look at it here. Its steric number is 6, and with this, that's how you bind 6 atoms to a central atom. Okay, and what is this called? That's an octahedron, a perfect octahedron. So each angle here is 90 degrees. This angle between this and that is 90 degrees, and this and that, and so on. You have 90-degree angles. All right, that's an octahedron. Steric number 6. Of course, there's 6 of them here. So now I need some help. Somebody who is not afraid of a little. Can you come, please? I have a needle here, but make sure not to hit me, okay? Can you destroy one of these balloons here, please? Yeah, use it at the back there. 1 only. Yeah. Thank you. Oh, it comes right in the right shape. Thank you very much. You can stick around if you want, but you can also sit down and take it up again. So what is this? What's the steric number now? We have 1 central, and so they should fill it with helium more, the top one, then I can breathe it actually. So this one is the planar here. That's trigonal, okay? And this is a pyramid here. So this is, what's the steric number? So there's 1 central, to 1, 2, 3, 4, 5 different atoms you can bind, all right? So this is 100, how many degrees is this here, each angle? 360 divided by 3 is what? 120, and this here is 90 degrees, okay? And from here to here is 180 degrees. So the steric number is 5, and this is a trigonal bipyramid, all right? So let's do the next lowest steric number, please. There you go, just hit it. All right. So, what's this here? That's funny. All right. Aha. Yeah, you have 4 faces here on this. And what's this called? A tetrahedron. Yeah, actually looks something like this here. A tetrahedron. So it's 4 corners here. And so you have 1 central atom bound to 1, 2, 3, 4 things. The angle between here is 109 degrees. 109 degrees. What's the steric number? The steric number is 4. If you have steric number 4, you only can have a tetrahedron. Remember though, if you have a free electron pair, that electron pair also counts. Okay? And it sits there free. There's nothing here to bind, but this is, I'm just showing you the electrons here, the electron pairs. And so now let's get to the next lower steric number. What would that be? Oh, see, it's much more forceful now. And so this would be, yeah, I have hydrogen in there. That would be a planar model, okay? So you have 1 central bound to 3 others. And what do you call this trigonal planar? And what's the angle between here, each of them? 120 degrees, all right? Remember that 1 pair can be a lone pair, or 2 can be a lone pair. But if you have lone pairs, they count. So let's remove the last one. Thank you, see. So now we have a linear molecule. This is the central, 1, 2, what's the steric number? And what's the geometry? Linear, okay? All right, let's finish it off. Just for the heck of it. Thank you. Ooh, okay, thank you. Thank you. So, see, you understand steric number now. And so let's give you some rules for the steric number. So this is called the valence shell electron pair repulsion model. VSEPR model. That's how you can determine these shapes. You make your Lewis structures, and then you see what kind of VSEPR geometry you have, and then you can tell what the shape of the molecule is, most of the time at least. So draw the Lewis structures for the molecule. Use any of the resonance structures to predict molecular structure. So if you have, because each bond, even a double bond, counts as 1. Okay? That's what it says here. Count each multiple bond as a single effective pair. Count electron pairs around the central atom. That's fine. And determine the position of atoms from the ways the electrons are shared and arrange them so as to minimize repulsion. We will come to that. So name the molecule structure from the position of the atoms. Okay? Of the atoms. And so let's do that here. Now this is a linear molecule, carbon dioxide. 2, 4, 6, 8. 4 on the carbon, perfectly fine. Linear molecule, carbon here. And so I have 1 and 1 here. Steric number 2, carbon dioxide.